This is a section on functions in the introduction to functions. So if you look at the top of your notes, there's some definitions. It says a function is an algebraic rule such that each x value corresponds to exactly one y value. So in other words, if you look at that little sketch there, we have our x values here, our y values here. So I have these x's and these y's, and each one of the x's only goes to one y. It's called mapping when you do that, when you draw the x's to the y's. So it doesn't mean that you have to have the same number of x's and y's, but each x can only go one place. The set of all the x values is called the domain, and the set of all the y values is called the range. So when you look below, it says representing a function. Let's look at 5 different ways we can represent the same function. The first one is as a set of ordered pairs. So what you have is the set of ordered pairs 1, 2, and then the point -2, -4, and the point 3, 6. That's one way we could represent a function. Each one of the x's, 1, -2, and 3, only goes to one y. The second way is as a mapping. So I can take my x values and put them in one little oval ring here, and my y values in another. So I have 1, -2, and 3. 1 maps to 2, -2 maps to -4, and 3 maps to 6. So there's the mappings inside. You can see when I did them inside the sets. That's another way. So as a correspondence or a mapping. The third way is something you're very comfortable with. That is as a table, only instead of calling it y, we're going to call it f of x, which means a function in x. So the -2 goes to the -4, the 1 goes to the 2, the 3 goes to the 6. You're used to seeing that. The next way we can do it, the fourth way, is as a graph. So I have the point -2, -4, which is right here. I have the point 1, 2, which is right here. And I have the point 3, 6, which would be up here. And if I then connected those, I would have a graph of that same function. So each of these things says the same thing, but in a different format. And finally, we can do it as a function. I get each y, each of my f of x's, I get by taking my x and multiplying it by 2. And you can see that's true from that table, so I can do it as an equation. What we're going to do first in the notes below, it says identifying a function. We're going to go through these examples twice, and the first time we're just going to decide is it a function or not. So let's look at example 1a. After we do that, we'll go back and we'll figure the domain and range. So I have my x values as 1, 3, 2, and 4. And then I have my y values as 1, 16, 4, and 9. 1 maps to 1, 3 maps to 9, 2 maps to 4, and 4 maps to 16. Each one of my x's only goes one place. So yes, that is a function. All right, we'll come back and do the domain and range of that one in just a second. Let's look at B. Here I have in my x's the numbers 1, 2, 3, and 4 again. And then in my y's, or my range, so domain and range, I have 3, 5, and 8. So let's look. 1 maps to 3, 2 maps to 5, 3 also maps to 3, and 4 maps to 8. Is it a function? Yes, it is. And yes, I realize that the 3 in the range has 2 things coming to it, but that's okay as long as each one of the elements in the domain only goes one place. And the 1 only goes one place, the 2 only goes one place, the 3 only goes one place, and the 4 only goes one place. It's okay if they go to the same place. So yes, that is also a function. We'll come back and do the domain and range. Let's look at C. Here we have it listed as a set of ordered pairs. We've got -2, -1, -1, 0, 0, 1, 1, 2, and 2, 2. I kind of ran out of space. So what I'm going to do, because I think it's easier to see it from a mapping, is I'm going to list all my x's here and my y's here, and I'm going to see how they map. So my x's are -2, -1, 0, 1, and 2. My y's, I have a -1, 0, and then I have a 1 and a 2. We don't repeat the 2. I know I've got a 1 and a 2 here, and then a 2 and a 2. You don't repeat it. You just write it once. So let's do the mapping. -2 maps to -1, so it goes one place. -1 maps to 0. It goes one place. 0 maps to 1. It just goes one place. 1 maps to 2. It goes one place. 2 maps to 2. It only goes one place. So yes, once again, that is a function, and we'll come back and do domain and range. All right, let's look at D, and I'm not going to write these this time. I'm just going to go ahead and put them in their ovals. So I've got my x's and my y's. The only x's that I have are -4 and -2 because one of them is repeated. And then my y's I have are 1 and 0. Now let's do the mapping. -4 maps to 1, so it only goes one place. -2 maps to 1. So far it only goes one place, but then -2 maps to 0. So you can see that -2 is going two places. So no, that is not a function, but we will look at its domain and range in just a second. In E, what you have two graphs. And I'm going to show you how easy it is to determine if something is a function when it's presented as a graph. You use what we call the vertical line test. And if I can draw a vertical line through that curve and it touches in more than one place, then no, it is not a function. Let's do it over here. I draw it through my graph. It touches in only one place, so yes, it is a function by the vertical line test. So that's easy if you have a graph to be able to do that. Let's look at this next one. We've got y equals 2x minus 5, meaning we have an equation. If I created an xy table, we know that every time I plug in something for x, I'm going to multiply it by 2 and subtract 5, and it's going to give me just one y. It's never going to give me two different y's. So yes, that is a function because every x only generates one y. We'll come back to domain and range. And finally, we have x squared plus y squared equals 1. This one's a little harder. So what I want to do is I want to solve this for y. So I'm going to subtract an x squared, and I get y squared equals 1 minus x squared. Take the square root of both sides, and I get y equals, remember, plus or minus square root of 1 minus x squared. Well, what does that tell me? That tells me that every time I plug in an x value, I'm going to get two different y values. I'm going to get the plus value and the minus value. So it's going to give me two different y's. So for example, if I put in a 0 here, I would have square root of 1 minus 0, and I would have the positive of that, which is 1, and I'd have the negative of that, which is negative 1. So I would end up with two different y's for the 0. So is that a function? No, it's not a function because it generated two y's. All right, look at the bottom there of the back of those notes. It says find the domain of the function. The domain is the largest set of real numbers that can be substituted in for x. So it's all of your x values. So let's go back to each of these and let's find the domain and the range. So when we go to, and I'm talking about example 1a. So when we go to example 1a, and we had our mapping, 1, 3, 2, 4, 1, 16, 4, 9. We said, yes, it is a function. Its domain is just that list as a set of x values, 1, 2, 3, and 4. And the range are the y values, 1, 4, 9, and 16. I put them in order from least to greatest. Same thing with the next one. In B, the domain here is 1, 2, 3, and 4. and our range is just 3, 5, and 8. In C, again, it was a function. The domain is -2, -1, 0, 1, and 2. And the range is -1, 0, 1, and 2. All right, in our next one, indeed, it wasn't a function, but I can see that the domain would have been -2 and -4, and the range would have been 0 and 1. All right. In E, it's not a function, so we don't need to worry about domain and range. And then on the second one, domain and range here is a little difficult. So let's take a look at this graph where we did the vertical line test and it only crossed in one place. Think about traveling from left to right across that graph. As it's going up, it is getting further and further left, and then as it's going up here, it's getting further and further right. So the domain here is -infinity to infinity. The range, however, is how far, what is the lowest point on that graph. And you can't tell by my sketch, but you can tell by your notes. The lowest point on that graph is a -3, and it does touch -3. So it includes -3. We show that with the bracket. But going up, in the up direction, it goes to infinity. Okay? In F, because this is a linear equation, and yes, it is a function, and the domain is -infinity to infinity, and the range is the same thing. The x's and y's can be anything. This one is not a function in G, so we don't need to worry about the domain and range there. You only need to worry about it when you're given a function. All right, let's look at the next page, which talks about restrictions on the domain, or domain restrictions. There's two situations where there's a restriction. One is when you have a variable in the denominator, that's the most common one, and two, when there's a variable under a radical sign. So let's look at a couple of those. Let's look at 2a. We're given the function f of x equals x squared plus 5x. Now let's check our 2. 1, is there a variable in a denominator? Well, no, because there's no denominator. 2, is there a variable under a radical? No, because there's no radical. Therefore, there are no domain restrictions. X can be anything. Let's look at B. Here we have g of x equals 3x over x squared minus 4. Well, we do have a denominator, and there is a variable in it. And we know that denominators can't be 0. So what we say is that denominator, x squared minus 4, can't be 0, not allowed to be 0. Now we just solve that as if it were an equal sign, and we get x squared can't be 4. Take the square root of both sides, and we get x can't be -2 or +2. Because if it was, put it back in here, you would see you would end up with a 0 in the denominator. So the domain restriction here is x cannot be -2 or +2. Let's look at C. Here we have h of t equals the square root of 4 minus 3t. And what do we know about square roots, even roots? We know that what's underneath has to be positive. So we know that 4 minus 3t must be greater than or equal to 0. It can't be negative. Now we just solve that. So we're going to subtract a 4 from both sides, and we get -3t is greater than or equal to -4. Divide by -3, and we know that when we do that, we flip the sign, and we get that t must be less than or equal to 4/3. So that is the domain restriction, that t must be less than or equal to 4/3. Now, so what does that mean? Is the domain, it means the domain is, there's the restriction, here's the domain. It's everything else. So it's the set of all t such that t is less than or equal to 4/3. And let's go back to B, because I didn't put in the domain here. We just did domain restriction. Since the domain restriction was x can't be -2 or 2, then the domain for that one is everything else. The set of all x such that x is not plus or minus 2. So you can see that when you write them, the domain and the domain restriction are related and what they look like. It says use function notation and evaluate functions. So when a function is defined by an equation, instead of writing y equals, we write f of x equals, and it's read f of x. So instead of having a little xy table, that becomes an x f of x table. Same thing, means the same thing. Let's look at example 3. It says for the function f defined by f of x equals 2x squared minus 3x, evaluate the following. We want to know what is f of 3. Now I want you to take note of how I'm writing this. I wrote f of 3 directly under the f of x. So I can see that all of these x's are going to become 3's. So I'm going to go 2, take out the x, put in a 3, minus 3, take out the x, put in a 3. So I have f of 3 is equal to 2, 3 squared is 9, minus 9, or f of 3 is equal to 18 minus 9. F of 3 is equal to 9. So if you will write your function first and then write what you're looking for underneath, you can see that the x became a 3, so it has to be true every place you have an x. So let's look at b. We're using that same function. F of x equals 2x squared minus 3x, and we want to know what is f of x plus f of 3. Well, we just found f of 3 right there, and we know what f of x is right there, so it's going to be the f of x, 2x squared minus 3x, plus the f of 3 that we found, so plus 9. So that was an easy one. Let's look at c. Again, f of x equals 2x squared minus 3x. So we want to know what our 3 f of x is equal to. Well, if I multiply this side by 3, I have to multiply this side by 3. So it's going to be 3 times 2x squared minus 3x, or 3 f of x equals 6x squared minus 9x. Doing these is about being very, very, very organized. All right, again, I'm going to write the function. F of x equals 2x squared minus 3x, and now we want to know what is f of negative x. Well, note, wherever there was an x, I put in a negative x, so let's continue to do that. 2, take out the x, in parentheses, put negative x, minus 3, take out the x, put in negative x. Why do I keep wanting to make that a 2? Alright, so f of negative x equals negative x squared is just x squared, so 2x squared. A negative 3 times a negative x is a positive 3x, and I have it. Let's look at e. We want to know negative f of x. Oops, forgot to write the function, so let's write the positive one first. F of x equals 2x squared minus 3x. So negative f of x, if I do the negative on this side, I have to do the negative of everything on this side. And that would give me negative 2x squared plus 3x. I just distribute that negative sign to both pieces. All right, here we go with f. Again, let's write the function. F of x equals 2x squared minus 3x. And now what do we want? We want f of 3x. So everywhere there is an x, we're going to put in a 3x. So 2, take out the x, 3x, square it. Minus 3, take out the x, put in a 3x. So I have f of 3x equals 2. 3x squared is 9x squared minus 9x, or f of 3x equals 18x squared minus 9x. And notice how careful I'm being about using parentheses every time I take an x out. Next one is kind of hard. F of x equals 2x squared minus 3x, and now we want to find f of x plus 3. So everywhere there's an x, what am I going to do? I'm going to put in an x plus 3. So 2, parentheses, take out the x, put in x plus 3, square it. Minus 3, take out the x, put in an x plus 3. F of x plus 3 is equal to 2 times, we square this by FOIL, writing it twice if necessary, and you're going to get x squared plus 6x plus 9. If you don't believe me, FOIL that out and you'll see. Now let's distribute the negative 3 minus 3x minus 9. All right, we've got some simplifying to do. Distribute the 2, 2x squared plus 12x plus 18 minus 3x minus 9, or f of x plus 3 is equal to 2x squared, that's that, 12x minus 3x plus 9x, 18 minus 9, plus 9. Just a matter of being organized and very systematic with these. All right, on the next page, we're going to look at operations on functions. It says we can form new functions by adding, subtracting, multiplying, or dividing two functions. So notation used to denote these functions we're going to look at, and we're going to, it's defined for all x in the domain of f and g. So let's take a look. In your notes, you'll see f plus g of x. That happens to be equal to f of x plus g of x. I think these are kind of intuitive. F times g of x is equal to f of x times g of x. I can split them. F minus g of x is equal to f of x minus g of x. And finally, f over g of x is equal to f of x over g of x, provided g of x does not equal 0, because you would have a 0 in the denominator. So let's take a look at how this works.